Right, so this is the Physics Lab 3. So as an introduction, the purpose was to measure the mass of a black hole using parallel and perpendicular momentum principles, which I found the 8.47 times 10 to the 33rd kilograms. And then I also wanted to test the necessary velocity for the ship to escape a planet orbiting the black hole, which I found to be -3 10 to the 7th, 7.5 10 to the 6th, 0 meters per second. And in key physics, a review from previous labs is Newton's second law, which the net force is a change in momentum over time. And then velocity update and position formulas here we get into later. But the new physics is the objects with rotational motion, where we split the force components into those parallel and perpendicular to the direction of momentum. This is that principal equation, and keynotes are for parallel forces. They are responsible for changing the magnitude of the momentum, and they point in the direction of motion as in the name. And then perpendicular change the direction of momentum, but not magnitude. And these point towards the center of the object's circular path, which you will see in the video later. And then another thing is the gravitational force given by this equation, where g is a gravitational constant, m1 and m2 are the masses of the objects, and the r vector is the vector that points from the source to the system, and you negate that. It's a lot of algebra, but you negate it to get the proper direction of the force. And then gravity is an attractive force, and the net force on an object when there's more than two objects in a system is the sum of the attractive forces caused by each object on that object. These are the initial conditions for part one. The key thing here is the gravitational constant and the mass of the star. And then we see here how we use that. Here we are setting up or defining variables for momentum, time, and velocity so that we can say the net force is the total change in momentum over time, and then we split those up into parallel and perpendicular components here. And these are the arrows that give us this result. So as you can see here, the star orbits the black hole, and this magenta arrow here is the parallel component of the force. The gold arrow is the perpendicular force, and the cyan arrow is the net force. And you can see the magnitudes of these here. And then using the values we obtained in the equations from the previous slide, I see the average mass for the black hole here is 8.47 times 10 to the 33rd kilogram. And then for part one discussion, the path of the star, as we could see, was the green line. The perpendicular force points towards, parallel was the pink arrow in motion, net force was the blue arrow. And the magnitude, the key thing is the magnitude of the forces change as the star gets closer, farther away from the black hole, and so does the speed. And then the setup for part two, I used the black hole mass from part one, which is the average. I put that here, and then I have the constants and the masses. And then this initial speed right here is what I was aiming to find for this experiment, and I found it to be this value, as I said in the beginning. And then for the calculation loop, these basically mirror the gravitational force formula. First, you start with finding the r vectors, and then the forces using that and the equation. And then we use velocity update formula and position update for the planet and star to get this value, or this result. So, as you can see, the ship takes off kind of up and to the left, and then it gets sucked in by the black hole, and then is shot out by the gravitational force of between the black hole and the ship. And at the end, it is 9.76 times 10 to the meters away from the black hole. The planet's orbital speed is 7.3 times 10 to the 6 meters per second, and the orbital period is 2.32 hours, oddly enough. And I found the sufficient initial velocity to be -3 times 10 to the 7th, 7.5 times 10 to the 6th, 0 meters per second. So discussion, what does it mean? How does net force and its parallel perpendicular components differ from the rate of change of momentum and its? Well, by the equations discussed earlier, the net force is equal to the rate of change of momentum. But the parallel forces change the magnitude of the momentum, and the perpendicular forces change the direction. And then, what if the initial velocity of your spaceship, or what would your initial velocity need to have in order to enter some kind of orbit around the black hole? Well, it would need to be a smaller x velocity and a bigger y velocity, making it go more straight up. This would result in the black hole creating a force sufficient to cause an orbit. However, I was not successful in calculating this. I tried many values and I either got crashing or it shot off. But this is what I would need to do. Thank you.